I've expanded our container of fluid to make it a little bit easier to see here. Now, as a fluid, this is a liquid because a gas fluid would expand to fill up the container no matter how big it was, right? So we're looking at a liquid now. Let's imagine here's the top surface of the liquid, and we're going to come down to some distance h below the surface. Now at the bottom here, we're going to have some pressure from the surrounding fluid. That pressure is going to be pushing upward on the bottom of the fluid. At the top, we've got the atmosphere, so we'll have some pressure on the top of the fluid. We'll call that PO, due to the atmosphere. So this pressure up here is just due to the atmosphere. Let's imagine that the height of this column is some height h, and it has some cross-sectional area A. Let's look at the forces that are acting on this cylinder of liquid. First of all, let's define, say, upward as the positive y direction. Now, what are the forces acting on this in the y direction? Well, first we have the pressure from the bottom, which is pushing upward. That's the pressure. What's the force? Remember, pressure is force per area, so the force will be pressure times area. So the force down here will be P times the area A. That is the pressure in the positive y direction. At the top, we'll have a pressure in the negative y direction. The pressure is PO, the cross-sectional area is A, so we're going to have a force of POA. So, and that's in the negative y direction, so we'll have minus POA. But then we'll also have the weight of the fluid. So there's a weight of the fluid, and how much is that going to be? It's going to be mg. Say, here's the center, here is the weight of the fluid, which is going to be mg, and that's going to be in the negative direction, so minus mg. Okay, there we go. Now let's think about this. What is m? Well, let's for the time being imagine that the density of the liquid is constant. So we'll assume that the density is constant. That is only an approximation, as we'll see. We'll see why in just a minute. But let's assume the density is constant. So what is m? Remember, density was mass per volume, so mass will be volume times, the mass will be density times the volume. So the mass will be density times the volume of this cylinder. Now what's the volume of the cylinder? It's the area of the base, which is A, times the height, which is h. So this is going to be AH. So the mass will be rho AH. So let's rewrite this here. We'll have the force in the y direction will be PA minus P naught A minus M is rho AH and then times G. Now let's think about this. What is this net force? That's the sum of all of the forces acting in the y direction. If we look at this fluid, and if we were to just let this sit for a while, that fluid is not going anywhere. It's not moving. It's not circulating anywhere. It's just stationary. Well, if that column of fluid is not moving, what does the net force on it have to be? It has to be 0. So we know that this quantity must equal 0. Well, we've got one positive, two negative quantities. Let's bring them over here. So what do we have? We have PA equals P naught A plus rho A G H. And notice there is an A in each term. Let's divide off the A. And what do we have? We have P equals PO plus rho G H. There we go. This is a very, very nice result. And what does it tell us? It tells us that the pressure in the liquid increases because P is larger than PO. As we go down into the fluid, the pressure increases from the pressure at the surface by an amount rho GH, so that P increases linearly with H, assuming that rho is constant. Now, why is that an approximation? Well, if we think about this, as we go down, if the pressure increases, what happens if you increase the pressure on a fluid? Well, typically if you increase the pressure on a fluid, the density is going to increase. We just saw that with the bulk modulus. So we know as the pressure increases, the fluid, or the liquid in this case, is going to contract, which means what happens to the density? The density will increase. So in general, we know as we go down into a liquid, the density will increase, but often with liquids, water for example, that increase in the density is very, very small. Liquids often are very difficult to compress. Not so with gases. Gases can increase their density much more, but with liquids, the density is not going to increase very much. It increases, but maybe not very much. So it's a good approximation with a liquid for the density we can assume the density remains constant. So this is a very interesting, very useful, very simple result. The pressure, as we go further down in the liquid, increases from the pressure at the surface linearly with the height below the surface. Okay, very, very good. Let's just stick some numbers in here. Let's try this with water and see what we get. Let's imagine that we are looking at a column of water that is 10.3 meters. In other words, we come down 10.3 meters from the surface of the water. And we'll assume that the pressure on the top is 1 atmosphere, 1.013 times 10 to the 5th pascals. Let's figure out what's the pressure down here. What do we have? We know that P equals P naught plus rho GH, or 1.013 times 10 to the 5th pascals, plus rho, assuming this is fresh water, like we've said before, rho is 1,000 kilograms per cubic meter. We'll assume that's accurate to 3 sig figs, times 9.80 meters per second squared, times H, which we're assuming to be 10.3, and what do we get? This will be 1.013 times 10 to the 5th pascals, plus multiply that out, and what do we get? We get 1.01 times 10 to the 5th pascals. Essentially the same thing as the atmosphere at the top, 1 atmosphere. What do we get? 2.02 times 10 to the 5th pascals. In other words, when we come down 10.3 meters, sorry about that, when we come down 10.3 meters, we have increased the pressure by an amount that's the same as what the pressure was at the surface. So if you've ever gone swimming, if you go down 10.3 meters, that's quite a ways, about 31 feet or so. That's quite a depth. The pressure that you would feel from the water above you is the same as the pressure that we are feeling right now just due to the atmosphere. I've gone down to the bottom of a swimming pool that is much, much less than 10.3 meters, and I have really felt that change in pressure. Well, it's amazing to think that the depth of 10.3 meters would be an increase in pressure to what we are already experiencing now. So we are actually experiencing quite a bit of pressure, but because everything is equilibrated with the pressure on the inside of our bodies to the pressure on the outside, we're used to it, but it's actually a substantial amount of pressure that we are experiencing. The one other way of kind of getting an idea of how much pressure that actually is when that pressure is removed. So if you imagine a vacuum going from atmospheric pressure into a vacuum, the change that would be is something that's definitely something that you would notice. So it's very interesting exactly how much pressure we are actually experiencing right now. All right, very, very good. Let's take a look at something else that's related to this result about the change in pressure with depth. This result, that P equals P naught plus rho GH, leads us to a very, very interesting result. Imagine we have two different shaped containers, both with even or equal heights of the fluid and both with the same depth. What this is telling us is that the pressure down at the bottom only depends on the height of the fluid. So if this height, wow, that's just about one of the worst braces I've ever drawn. Do it from this side, there we go. If this height is the same as this height, then the pressure at the bottom will be the same. The pressure here is the same as the pressure here. Even though this obviously has much more fluid, how is it possible that the pressure here could be the same? What's supporting the rest of that fluid? Well, what we notice is that obviously we've got walls here of the container that are exerting forces on the fluid, and that's basically what is supporting the rest of that fluid mass. The sides of the container here are supporting all of that fluid. We don't have those slanted sides that need to support that fluid for this, so it does turn out that the pressures are exactly the same. Okay, very, very interesting. This actually leads to a very, very important result relating to the pressure within a fluid called Pascal's principle. Let me write that and we'll take a look at it. Pascal's principle, which is named after Blaise Pascal, who was a mathematician, physicist, who lived from 1623 to 1662, so contemporary of Isaac Newton. Blaise Pascal stated Pascal's principle, which is the pressure applied to an enclosed liquid is transmitted undiminished to every point in the fluid and to the walls of the container. So let's imagine we've got some container here that is full of some liquid. And we've got some piston here, so we can move this in and out to change the pressure acting on the fluid. When we have some pressure here, we are applying some pressure here, there will be pressure inside the fluid. Now, the pressure up the top might be different than the pressure at the bottom, as we've seen with the fluid. So we might have different pressures at different points. But if we increase this pressure by some amount delta P, then that increase in pressure will be the same increase in pressure as experienced at every point in the fluid and on the walls of the container. So the pressure everywhere, inside and around on the walls, will all increase by the same amount. Pressure applied to an enclosed liquid is transmitted undiminished, so an increase in pressure. We're not saying that the pressure at every point is the same, but that change in pressure will be transmitted undiminished to every point in the fluid and to the walls of the container. Okay, that is a very, very important result, and it leads to an extremely important use of applying pressures to fluids called hydraulics. Let's take a look at that. Let's imagine we have a very peculiar shaped container that looks something like this, where this is a container here where we've got two openings. There's an opening over here, a large opening, and an opening over here, a smaller opening. And we've got maybe a piston over here, like a stopper that can move up and down over here, and one over here that can move up and down over here. Let's assume this one has some area A1, while this one has an area A2. And we're going to assume, as I've drawn them, that A1 is less than A2. Let's imagine that they are at equal pressures, so the stoppers, the pistons, are not moving. But now let's apply a force over here. Let's apply an additional force over here, pushing down of F1. Well, what have we done? We've increased the pressure. We've increased the pressure over here, and the increase in the pressure over on this side is the force per area, or F1 over A1. Well, what does Pascal's principle say? An increase in pressure over here has to be equal to the increase in pressure over here, undiminished. In other words, we're going to get a higher pressure over here. If we push down over here, the fluid is going to push up over here. This is going to push up with a force, we'll call it F2, but the pressure over here has to be the same as the pressure over here. So P2 over here, which is going to be the force per area, F2 over A2, these two pressures have to be the same. That's what Pascal's principle is telling us, that the increase in pressure over here has to be equal to the increase in pressure over here. In other words, F1 over A1 must be equal to F2 over A2. In other words, let's bring the A2 over here and the F1 over here. What we have is A2 over A1 must be equal to F2 over F1. Okay, right? F2 over F1, A2 over A1. So what does this tell us? Well, if A2 is larger than A1, if A2 is larger than A1, F2 must be larger than F1. So the force that we get out of this piston that pushes up must be larger than the force that we apply over here. And if we make these tubes very, very different, imagine rather than A1 less than A2, A1 is much less than A2, then A2 is much larger than A1, F2 must be much larger than F1. F2 is much, much larger than F1. So what happens? By putting a very reasonable force over on this piston, on this tube over here, we get a much, much larger force over on this piston. Well, that is a very, very interesting result. And the use of this is, as I said, what's called hydraulics. If you drive a car and you've ever taken a car to a service station, you might have seen the car gets driven up on some tracks that hold the wheels, and then this giant piston at the bottom lifts the whole car right up in the air. Well, that's basically this piston here moving up, lifting up your car, so that by applying a very reasonable force on a hydraulic tube, a tube filled with liquid, hydraulic fluid, by having a pump that puts a very reasonable force over here, you can get a much, much larger force, enough to lift up a car, over here. Or you might have seen hydraulic pistons on crane arms or lifting up beds on dump trucks or something like that. That's what's going on. By using a pump that increases the pressure in the hydraulic line, that increase in pressure can be used to create a much, much larger increase in the force that can then be used to do all sorts of things that require large forces. Here are some photographs of a hydraulic digger that I happened across shortly after recording this video, and I just thought I'd point out some of the hydraulic aspects of it. Here you can see the hydraulic piston that's being forced out of this column here with the hydraulic lines feeding the hydraulic fluid in, pushing the piston out here. As this gets pushed out here, that's going to move the bucket in this direction here. Here's another view of the side. Here's another hydraulic piston being pushed out here. When this comes out, that's going to swivel the bucket around, and you can see all the hydraulic lines here. And one more view over here. There's the hydraulic piston here that pushes the plow up and down here. And again, you can see the hydraulic lines here and here. Very, very good. Okay, now let's take a look at some methods of measuring pressure. How can we measure the pressure in different situations? We'll look at a couple examples.